Welcome back to Understanding Signal Isolators, Converters, and Interfaces. In Part 1, we laid the foundation for understanding why signal isolation is essential in modern process control. We reviewed how isolators break the galvanic path to eliminate unwanted electrical interactions, keeping measurement signals stable, accurate, and immune to plant noise. We also covered how ground loops form, why they remain one of the most persistent causes of signal error, and how isolators solve the problem by interrupting the current path between different ground potentials. We introduced the core isolation methods, optical and transformer isolation, and explained the importance of choosing two-way or three-way isolation based on your application. Without groundwork in place, we're ready to go deeper in Part 2. In Part 2, we're taking the next step and looking at how signal isolators are powered, because the way an isolator receives power determines what it can do in your loop. We'll introduce the two main families of isolators: 4-wire units that use external power to drive heavier loads and handle voltage, zero-based, and even bipolar output signals, and 2-wire loop-powered isolators that run directly from the process loop and offer simpler, lower-cost installation. We'll also look at where each type fits best, and why choosing the right power architecture is essential for reliable, accurate signal conditioning. By the end, you'll have a clear picture of how 2-wire and 4-wire isolators differ, and why that difference matters in real applications. Before we dive deeper into how signal isolation works, it's important to understand that not all isolators are powered the same way. In fact, the power architecture is one of the most critical differences between isolator types. In this video, we'll focus on the two major types: 4-wire, line-powered isolators, and 2-wire, loop-powered isolators. These designs behave differently in the field, support different types of outputs, and have very different load and compliance characteristics. Choosing between them isn't arbitrary. Your application and the available loop power ultimately determine which architecture will perform reliably. Let's start with 4-wire isolators. These devices use an external power source, typically 24 volts DC or AC mains, to energize their electronics and output stage. Because they don't rely on loop power, 4-wire isolators can support signal types that loop-powered designs can't, such as voltage outputs like 0 to 10 volts, zero-based signals such as 0 to 20 milliamps, and even bipolar ranges such as minus 10 volts to plus 10 volts. They also provide significantly higher drive capability, usually around 1,000 to 1,200 ohms, with some models reaching up to 1,800 ohms. This makes them ideal for long cable runs, high-impedance receivers, or applications where the measurement loop includes multiple devices in series. In short, if you need flexible output formats, high load driving capability, or complete independence from loop power, a 4-wire isolator would be the ideal fit. Now, let's look at 2-wire isolators, which operate very differently. Instead of using their own power source, these isolators draw power from the loop itself. This eliminates the need to run additional power wiring and makes them extremely easy to install. Often, you simply break the loop and insert the isolator. There are two main types: output loop-powered isolators, which behave like standard 2-wire transmitters and always produce a 4 to 20 milliamp output, and input loop-powered isolators, which are powered by a line mains-powered 4-wire transmitter upstream. Output loop-powered OLP isolators, which are powered on their output side by the receiving device, are the most common type of 2-wire isolators, and typically have a very low input impedance of around 50 ohms, so their installation in an existing loop is typically less burdensome. Input loop-powered ILP designs are a little more nuanced, and special care must be taken to ensure they don't jeopardize the loop's available compliance voltage. These units consume about 5.5 volts from the input side of the loop, equivalent to a 275 ohm load, and can only drive into an additional 0 to 250 ohms on their output. If the total burden approaches the transmitter's compliance limit, accuracy and operation can suffer. When applied correctly, though, Two-wire isolators provide clean, cost-effective isolation with minimal wiring and fast installation. When it comes to real-world applications, four-wire and two-wire isolators each have clear strengths. A four-wire isolator is the right choice when you need higher drive capability, long cable runs, high impedance receivers, or when your output must be voltage, zero-based, or bipolar. These units operate independently from loop power, making them ideal for complex systems and demanding signal conditioning. On the other hand, two-wire isolators are perfect for simpler loops where installation time and wiring costs need to stay low. They fit best in standard 4 to 20 milliamp applications, retrofit situations where isolation needs to be added after startup, and loops where the transmitter has enough compliance voltage to support a loop power design. Matching the isolator to the application ensures accuracy, stability, and long-term reliability. Power architecture affects how accurately an isolator can reproduce the measurement signal. A four-wire isolator has its own power source, so it maintains full output drive and stability even with heavy loads or long cable runs. A two-wire ILP isolator, however, must operate within the loop's limited power budget. Every volt it consumes reduces the transmitter's available compliance voltage, and if the total loop burden gets too high, the signal can distort or fail to track the full range. While two-wire OLP isolators have a very small burden on the input side of the loop, care should be taken to ensure that its power requirements can be met by the receiving device's power supply budget. Choosing the right architecture ensures the isolator delivers clean, reliable performance without overloading the loop. In this video, we explored how power architecture shapes the performance and application of signal isolators. We looked at the differences between four-wire and two-wire designs, why four-wire isolators are ideal when you need higher drive capability, flexible output formats, or independence from loop power, and why two-wire isolators offer quick, low-cost installation when loop power limits are respected. We also covered how each architecture fits best in real applications, and how power constraints directly impact signal accuracy, stability, and full range performance. Understanding these distinctions ensures you select the right isolator for your loop and maintain clean, reliable measurement signals.